Hi, everybody. This is Mr. Zarzak, and in this screencast, I'm going to talk about this concept of energy. All right, so let's get started. Before we can get into energy, okay, it's necessary for us to do a quick little review of work, which is the product of force and displacement. Okay, and we've done some examples with this. When it comes to work, okay, where do we get this equation from? Well, there's a derivation for it, but we can also think of it as just we kind of put things together in physics and see what comes out. And sometimes you get something and sometimes you get nothing. With work, where we put together force and distance. Now, it's true that force and times displacement is work. Okay, the product of these two does, in fact, tell us something. Force divided by distance or displacement doesn't tell us anything at all, unfortunately. Okay, so when we talk about equations, sometimes the way that we put the variables together gives us something useful and sometimes not. All right, and the same is true with graphing. Right, so I decided to take force and distance and put it on a graph, and just very, very simple graph, just a straight line going across, just so that we could talk about it and see if there's anything more we can discern from this. Now, if we were going to work out the slope to this, I mean, the line is flat and horizontal, so it's got a slope of 0, but in terms of the way that we calculate the slope would be the change in force over the change in distance, and that doesn't tell us anything, okay? However, the other trick that we use in physics is we look at the area underneath a graph, okay? And if we do that, all right, well, the shape is just a rectangle, all right? And to find the area of a rectangle would be taking, base times height or length times width, or in this case, force times distance, which means that the area underneath an FD graph is equivalent to the work. Okay, so the area underneath an FD graph does, in fact, tell us something very useful. It tells us the work that gets done on some object that experiences a force and gets displaced some distance. Okay. Speaking of graphs, this is a good opportunity for a little bit of review here. So for this FD graph, okay, for this shape that looks like this, that's flat and has this 0 slope, um, we would like to know what does the corresponding DT, VT, and AT graph look like. So this is something that you should try for yourself, just what the shapes are. So go ahead and pause the video, give these a try, and then when you think you have an answer, play the video and I will show you what the three graphs look like and how to get the correct shapes. Okay, so how do we do it? Well, of the three graphs, it's actually going to be the easiest to start with the acceleration time graph. The reason being is because we know from Newton's second law that force is equal to mass times acceleration. All right, we say that these two things are directly proportional to one another. What separates acceleration and force is a coefficient that we just call mass. So acceleration and force graphs look exactly like one another. They're just scaled by a factor of the mass. All right, so all that means is that if this force graph is flat like this, it has a 0 slope. Well, that's going to be the exact same thing for the acceleration. The acceleration graph is going to be flat and have a 0 slope as well. Okay, what exactly the value of the acceleration is, we don't know. There's no numbers on this graph, but it would be whatever the value of the force is times whatever value that the mass is for the thing on which the force is acting. Okay, this has a 0 slope, but it has a non-zero value, so we are talking about a thing that's experiencing acceleration. If we look at the velocity time graph, you might remember that the slope of a velocity time graph tells us the acceleration. The acceleration is positive and constant. It's some numerical value that's a positive number that stays the same. So the slope of the velocity graph is positive and constant. What would that look like? It would just look like a straight line. Okay, a straight line that is increasing in value but constant in slope. Okay. Once we have the velocity graph, we can then get the dt graph. You might remember that the slope of the dt graph is the velocity. So we have to look at the velocity graph and say, what's the velocity doing? Okay, so if I look at the velocity graph, the velocity values are all positive, and the values of the velocity are getting bigger with time. So that means that the slope of the dt graph is positive, and that the slope is getting larger with time, which means that we're looking at a curved graph. Okay, what does that curve look like? It's going to look something like this. Okay, it's going to have a positive value. All right, so the slope goes up and to the right. Okay, and the magnitude of the slope gets larger, so we can see that this graph is getting steeper, and so that slope is getting larger and larger and larger. Okay. So what if I go ahead and change up, all right, my graph a little bit? So I'm now going to look at this blue section here, okay, where the force is getting bigger with time. What would the corresponding dt, vt, and at graphs look like this? Okay, so this is another one for you to try. So go ahead and pause the video and see if you can figure out what these graphs look like just for that blue section. We already did the red section, so just focus on the blue. All right, give it a shot. Okay, so hopefully have your three shaped graphs sitting in front of you. And just like before, we're going to start by looking at the acceleration graph. All right, because force is equal to mass times acceleration. So whatever the shape of the force graph is, that's the shape of the acceleration graph too. So that's just going to be a line that goes like this, okay? Constant positive slope for the acceleration. All right, now if we go back to the VT graph, all right, the slope of the VT graph is the acceleration. The acceleration is positive and increasing, so the slope of the velocity graph is positive and increasing. So it would be a curved graph that would look something like this. All right. Now, what about the dt graph? All right, well, the slope of the dt graph is the velocity. So if we look at the velocity is positive and the velocity is increasing at an increasing rate. Okay, so the slope of the dt graph is positive and increasing at an increasing rate. So what's that going to look like? It's going to look like another curve, but it's going to be a curve that goes up even more quickly and steeply than the VT graph, okay? Just to give you an analogy, if you had a graphing calculator, okay, the acceleration time graph would follow some function that will look kind of like, say, like y equals x, okay, just to get the basic shape. That's a linear function, okay? For the VT graph would follow a trend similar to a y equals x squared graph, okay, and then the dt graph would look similar to a function that follows an x cubed kind of a pattern, okay? So there's a little bit more to it, but that just gives you the basic shapes, all right? So anyways, that's all I wanted to say about the graphing. That's more than enough for now. Let's move on to connecting this all to energy, okay? So we've previously discussed that when we do mechanical work, all right, one of the ways in which mechanical work can be done is to lift something. And when you lift something, you are doing work against gravity, okay? So if we talk about the simple idea of work is equal to force times displacement, all right, well, if our displacement is directly upwards, we call it like a dy, like our vertical displacement. Okay, well, that gets done by applying a force in that vertical direction. So a y force in the y direction gives us a y displacement. Okay, now with vertical displacement, the common name that we give to that is just, well, height. Okay, and when we lift something, all right, just to lift it, we've got to provide just enough force to equal out its weight. Okay, remember that the weight is the force of gravity. Okay, that we say the weight is equal to mg. Okay, so again, we're not going to accelerate it as we lift it. We're just going to provide just enough force to lift it straight up. Okay, and move it along at a constant speed upwards. All right, and the amount of force that's required to do that is the force of gravity, or its weight. Okay, to put it in simple terms, if something weighs 100 pounds, well, then you need 100 pounds in order to lift it. Okay, so if I take that vertical force and multiply it by that vertical distance or that height, okay, I said that this work can be calculated as mgh. Now, again, this work is just the force of gravity, okay, times the height. Okay, if I break down the force of gravity, that's mg, so we get this mgh. All right, and when I lift something, okay, I'm actually increasing its energy. Okay, and that's an important concept here, all right? Whereas the way that we calculate work is we take force times displacement. Okay, well, that's like an equation that we can use, but something more powerful is the definition of work, which is the change in energy. That's something that's more fundamental, okay, than just the W is equal to F times D. Okay, the way that we would express this mathematically is to say work is equal to change in energy. That's W is equal to delta E. That delta, okay, is Greek for delta, but it signifies a change in a value. And I remind you too that when we do change in, it always follows the same format. Okay, whatever our final value is minus whatever our initial value is. Okay, but this right here, this is the real equation for work in that it gives us the definition of work, which is the change in energy. All right, this work that gets done to lift something, okay, we call this potential energy, because the higher it is in the air, the more potential it has to do work on something later by being dropped, or in this case, on this picture, released down the ramp. All right. Um, the unit of energy is the same as the unit of work, which is the joule. Okay, so the reason for that is, think about it like money. Okay, here in the U.S. we use dollars. That's the unit for the money. Okay, well, we can have money or we can have change in money. I gained money. I gained $10 versus I have $20. I lose $10 excuse me, versus I have $5. Whether I'm talking about the change in or the value, the unit is the same. It would be the dollar. Well, when we talk about work and energy, it's the same thing. All right. Whether I'm talking about the change in energy or the value of energy, I'm talking about the joule. Remember that the change in energy is just the work. Okay. So that's kind of neat. When we calculate potential energy, we go MGH. Now, a pitfall to avoid or something to watch out for is when we calculate potential energy, we plug in a value for gravity that's positive. So whether we're talking about 9.8 or 10, we would put that in for the G in the equation, but we don't use negative. All right, now why is that the case? Why do we not use a negative here? All right, well, first thing is that energy is a scalar value. It has no sign. It is not a vector quantity. Okay, mathematically, the reason it works out this way for potential energy is as well, mg is the weight. All right, so like if I took here's a thing. Oh, give me a nice, pretty free body diagram. Okay, so if I was going to diagram out the force of gravity, okay, well, we know that this points down. All right, if I released it, it would accelerate downwards, and that's where we get this idea of negative 9.8. Okay, it's pulled downward by its mass times negative 9.8. Well, we're not talking about letting the thing go downward. We're talking about lifting it upwards. Okay, so the force that we have to apply is going to be in the exact opposite direction of gravity. So, if we take something and we pull it upwards, we need to apply a force this direction, okay, in the exact opposite of the weight. All right. And so if we think about this, all right, what we'd really be doing here is if we were going to use negative 9.8, we'd take like the mass, times negative 9.8 or negative 10. Okay, but this force that we need to apply is we need to apply a force in the exact opposite direction of the weight. That's our force. Okay, in which case, well, we'd have a negative times a negative is equal to a positive, and that's always going to be the case. So because that's always going to be the case, we're just not going to bother putting either of these negatives in because it's kind of a waste of time. Okay, so I hope that helps you understand why. But again, when we talk about energy, okay, energy is a scalar quantity, so we're not going to plug in any negatives into the M to the G or to the H. Okay, all right. When we're talking about potential energy, one of the other pitfalls or things that we have to be very careful of is the way that we reference our height. So we say that potential energy is relative to how we reference our zero height. Okay, so like if I took this cart and I towed it up to the top of this ramp, okay, well, it might be very reasonable to say, all right, well, it went from from down here to up here, right? This is its change in height. Okay, in which case, like down here, this would be like our height is equal to 0. Okay, if we let the car go, it would go down the ramp. Okay, back down to the table, back to our 0 height here, which is totally fine as long as we don't let the cart leave the table. Okay, but what if we let the car come down to the bottom of the ramp? And then we let it roll off the table to down here to the bottom of the page. Okay, well, if down here is where the car lands, well, now that becomes our 0 height. Okay, in which case, at the top of the ramp, okay, the car is much higher. All right, so we're just changing our 0 reference height. We put the H is equal to 0. Oops. Come on back here. Erase that so it looks nice. There we go. So we're putting our height, our 0 height, down there. Okay, are we allowed to make those changes? Well, within the context of a particular problem, okay, once we reference our 0 height, we have to stick to it. So it's really dependent upon, does the cart go off the tabletop or not? So that's really the important factor. If it never does, well, then why not make the tabletop 0? Why go through the trouble of making all that extra measurement? If it does go off the table, well, that's a problem. We have to measure down to the ground because, well, height can't be negative. Potential energy can't be negative. Okay, so just something to be aware of and be cautious of. All right. We have also heard that the evidence of doing work is not just to lift, but can also be done to accelerate. Okay, so if we make something speed up or slow down without getting higher or lower in the air, okay, well then we're not changing the potential energy. We'd have to go higher up to increase the potential energy, lower down to decrease it. Okay, so what if we're doing neither of those things? All right, well then we have a different variety of work and we wind up with a different variety of energy. All right, so let me show you what I mean by that. If we start with work is equal to force times displacement, okay, well then if the object is accelerated, we can expand out F to F equals ma, so we'd be taking ma times d. All right, now within this, we've got this acceleration, okay, so this is using work. All right, if I combine this with kinematics, so what I mean is I got a whole bunch of motion equations, all right, one of which is this, vf squared equals vi squared plus 2AD. We call this the timeless equation because it doesn't have any time in it. Okay, I'm going to rearrange this equation to solve for acceleration. So VF squared minus VI squared is equal to 2AD. All right, and then I'm going to take and divide out the 2D over to the left side. So I get VF squared minus VI squared divided by 2D is equal to A. Okay, and I'm going to take this and I'm going to substitute this expression into the acceleration over here. All right, so now watch what happens when I do that. Okay, so then I say work is equal to mass times VF squared minus VI squared over 2D times D. Okay, notice I now have a D, a displacement in the numerator and the denominator, so that factors out. Okay, and I'm left with work is equal to mass times quantity V F squared minus VI squared over 2. Okay. Now this kind of simplifies down in that, let's say that we took our cart and we started it from rest. Okay, we can simplify the equation. If we start from rest, that just is a fancy way of saying our VI is equal to 0. Okay, in which case we'd have work is equal to mass times final velocity squared divided by 2. Okay, and it's kind of customary to take and that divide by 2 and just pull it out to the front and write it as a 1/2. Okay, leave the mass and just say, all right, some velocity at some point squared. Okay, and then this expression right here, work done to accelerate is equal to 1/2 mv squared. All right, that work, remember that work is the change in energy. Okay, we have a special name that we give to work that gets done to accelerate, or specifically the change in energy that occurs when something accelerates. Okay, acceleration causes something to move, all right, and so we call that energy of moving kinetic energy. Okay, so kinetic energy is equal to 1/2 mv squared. All right, so we have kinetic energy half mv squared, and we have potential energy is equal to mgh. Okay, so those are our two energy types that we'll be working with in terms of mechanical energy. Okay, and then a little bit later on too, okay, we're going to call this gravitational potential energy because we can have other types of stored energy, but that's a conversation for a little bit later. All right. One other thing about kinetic energy, okay, in the game of kinetic energy, the energy of motion, it's mass and velocity dependent. Okay, but the velocity part has a greater influence on the energy than the mass because it gets squared. Okay, and so here, so look at this. It says compare the work to get an object from V to 2V. Okay, so if something is moving with some velocity V, we don't care, how fast it is. It's just from some speed in some direction. Okay, if I want to double that, okay, look what happens to the kinetic energy. Okay, the 1/2 is still out front. That's literally just a constant. Okay, the mass doesn't change. It's another constant. Okay, but the velocity here goes from V to 2V. Okay, and in the equation, the velocity gets squared. Okay, so by introducing that to say, well, like by what unknown factor, we'll call that like x, okay, does the velocity change? And really the v is still there, so I'm just going to make that I'm going to make that blue just so you can see that we're really just changing, okay, that coefficient. All right, but that velocity gets squared, so whatever happens to the v happens to the coefficient in front of it. Okay, and so this x that I'm talking about is 4 because that's 2 squared. I get 4 times the kinetic energy, m times 4v squared. Okay, so again, in the game of kinetic energy, okay, doubling the velocity quadruples the kinetic energy. If I go 3 times faster, I have 9 times the kinetic energy. If I went 4 times faster, I have 16 times the kinetic energy. Okay, versus like changing the mass, something that's twice as mass is moving at the same speed will only have twice the kinetic energy. Okay, so again, the velocity is the more important factor. All right, well, anyways, now that we have the potential and the kinetic energy defined and we have equations for them, that's the pieces that we need to begin to work with the law of conservation of energy that just says that the total amount of energy can never be created or destroyed. It's only transformed from one form to another. Okay, so that's a concept and a law that's worthy of its own video. So we're going to say that that's enough for this one. So Mr. Zarzak says, thank you for watching, and I will see you next time.